Hello everyone, welcome to FAANG tastic solution. So today we'll be solving validate binary search tree. So we need to validate, whether given a tree is a binary search tree or not. So let's read the question first, then that will make the clarity like whether some tree or binary tree or not. So it says given the root of a binary tree, so we'll be given an input array, but for our function we'll be having the root of the binary tree, which is nothing but the 2. We need to determine if this tree is a valid binary search tree or not. Now, what is the definition of binary search tree? It says the left subtree of a node contains only nodes with the key less than the node's key. So if my root is 2, so on the left subtree, entire tree, it's not only the left node, we are talking about the left subtree, should be the less than the current root value. So that means if here we have 2, the left subtree should be less than 2, that is 1 or anything else. It cannot be even equal to that. Similarly, the right subtree of node contains only nodes with greater than the node's key. So if we are going to the right side, we can have any values greater than 2, which is let's say 10, 20, anything out of that. Both the left subtree and right subtree also should be the binary search tree, and the same thing criteria should be applied to the left subtree, whatever we checked on this particular node, and onto the right subtree as well. Then only we can say given a tree is binary search tree or not. So in this example, if you see on the left hand side, we have only one node 1 and right side only one node 3. And this is less than 2, this is less than 3. And so this is a valid binary search tree. If we see there, their children's on the left and right for this one, that is null value, right? So we can ignore that. So we know that this entire left subtree is also binary search tree, and right subtree is also binary search tree. That's why this given tree is binary search tree. What about this one? So in left, we can see it's validating the criteria. The left subtree is valid binary search tree, but what about the right? Right subtree should have been greater than 5, but we see this value is 4. So that's why here it's not validating and we are returning the false. Let's look into one more example. So this will make more clarity now. So let's say if we have given subtree named as, it has value root as 7. On the left hand side, we have value as 3, and right side we have value as 8, right? So this look like this and this are validating the criteria of the binary search tree. But what about the left and right of these three? So this left is less than 3, which is 2, looks good. Right is greater than 3, right? But it's not true. Even though it's greater than true, this value should have been less than this root value, because what our criteria is, entire subtree should also be binary search tree. What do we mean by that? On the left hand side of the 7, every value should be less than 7. So the value should be less than 7, and here the value should be greater than it. But this 9 is not less than 7. That's why this subtree won't return a true for us. This is a not valid binary search tree. So that's the criteria to know whether some trees are valid binary search tree or not. We cannot just determine based on the current root node and see if it's left side is less than the current value, right is the the greater than the current node. Similarly, just here again match the left node is less than the root node, and right is greater than root node, then return true. That is not the correct way to look into that. We should always look whatever the current node we are, that should have the valid value. That means this current value 9 should belong to some limit. So like limit for this 9, if you see, the maximum value it can go to 7, and the minimum value it can go to 3, right? So any valid number between 3 and 7 could have been a valid number. So if I had written here 6, this could have been perfectly the valid binary search tree. Because if you see on the left hand side of 7, every value like 3, 2, 6 is less than 7. And similarly for this particular 3, if I see on the left hand side everything is less than 3, right hand side everything is greater than 3 and less than this parent root node what we had the value. So now we know that for any node we need to determine the proper maximum and minimum value which it can belong to, and that's the only criteria to know whether certain tree is valid binary search tree or not. We cannot just determine based on this current node, if it's greater than this value and less than this value. We need to know the proper maximum and minimum values to determine the current node value, whether this node value is correct or not. We cannot just go and compare with this current node. We need to compare with some this maximum and minimum values. So just to reiterate, at this particular place, if you see quickly analyze, this can only belong to 3, 7. Like the maximum, it should always be greater than 3, and less than 7. Then only it would be valid binary search tree. If its value is 2, right, less than this minimum value, then again this is not a valid binary search tree because this is breaking this condition of this root node. And if it's going to, let's say, 8, so even though it's greater than this current node, it's not less than this particular previous root node value. So that's our end goal. For each node, our goal should be to determine some min and max value and know whether the current node is falling in between this or not. If this is not falling between this min and max, then we can say return false. If it's falling between this, then we can return true. That should be our end goal to determine. So now let's look into the example, one more example, how we can determine. So if we have an example 20 in left hand side 10, 5, 15, and then right side we have 30, 22, and 35. So this is a valid binary search tree for us. We are going to return true, but how we are going to do that? So let's just assume for the very first time when we are at the root node, right? We are initializing some min and max value. It can be integer dot min, integer dot max, right? Anything, but we have some min or max values. So that means it will belongs integer like minus infinity to till the infinity, right? It can belong to any number on the very first root node, which we are good. But let's go towards the left side, right? The moment we are coming to the left side, we know that this particular value, it should be less than the 20. So it can be, the minimum value can be anything till minus infinity, right? Anything, whatever the integer dot min value we have defined, right? It can go towards any minimum value, right? But what about the maximum value? Maximum value it can 20. That's the only thing it can take, right? So how do we determine that? So now we know that if we are going and making it 21, then it won't be a valid binary search tree. So current value 10 is falling between this bracket, right? So we know that this is good. So how did we determine this? When we are coming towards the left hand side, whatever the minimum and maximum value we have determined in the previous root node, we are saying the minimum value would be, if you see the minimum value of this left side would be equals to whatever the minimum variable which we had. And what about the maximum value? Maximum value is coming from this previous root dot value. Whatever the node we have, that node dot value. So on left side, what we are doing, if you are going to the left side, min would be whatever the min we have in the previous value, and the maximum value it can take would be whatever the current node dot value. That's the thing, right? Let's quickly verify again towards the left hand side. If you're coming here, right? So if you're coming towards this side, so minimum can be again minus till minus infinity, but the maximum should be only till 10, right? So which is again minimum is coming from this particular min value, and the maximum is coming from this root dot value, whatever this current node dot value we have, right? Let's go towards the right side now. If you're going towards the right side, so again for the min and max, the max it can take any value, right? Towards the infinity. So initially we are initializing this max with, let's say, some infinity value, right? So whatever the maximum value we have initialized, that max is coming here. If you see this max is coming here, it can take any value greater than 20. What about the minimum value? Minimum it can go till 20, right? So this minimum value is coming from this root dot value. So for the right, the minimum value would be the current node or root dot value, and the maximum can be whatever the previous maximum we had initialized, that is coming here. Now let's go again one more right side. So if you are coming here again, the maximum it can go anything greater than 30, which is the maximum value, which is coming from the whatever the previous node we had passed the maximum value. Whatever the minimum it can't be less than 30, right? So the root dot value is the minimum value, and the maximum is whatever the maximum coming from the parent side. Now let's go again towards the left side and see, can this verify the same criteria? So if you're going towards the left side, min would be whatever the previous minimum value we had. So like if it's a 30, it cannot be less than 20, right? Because on the previous, see here, the root value had 20, right? So whatever that value came towards for this minimum, this cannot be less than 20. But what about the maximum? Maximum would be the root dot value, which is 30. So which is looking correct, right? It can have any value between 20 to 30. It cannot be 18. If you're saying 18, that means it's less than this root node. So it cannot have the 18 value. It can have anything value greater than 20. And it cannot have any value no greater than 30 because it's going towards the left hand side of this particular node. So now this is the crux of the solution. We need to determine the what should be the minimum left and the maximum right value, and then we can quickly solve this problem. So now if we know the solution, let's quickly write the program for this one. How we can write this. So let's write a function for this. Function is valid or something. It's is bst, which will take the current node, whatever the node is coming, and some min and max value. So if root is equals to null, if the current value is null, then we just need to return true. Otherwise, when can we return false? If it's not falling, for this left hand side and right hand side, if it's not following this condition, then we can return the false, right? So let's say if min is not equals to null and root dot value is less than equals to minimum, right? So my current value is less than going to the minimum. So anytime, whatever the minimum and maximum value we have given, this root dot value shouldn't be less than equal to this minimum value and cannot be greater than this value. That's what we know always. Whatever the minimum and maximum value we have defined, this should be inside that boundary only. If it's going outside this boundary, the minimum and maximum value, we have to return the false. So that's what we are going to write. So if min is not equals to none and root dot value is less than equals to minimum, or similarly for the maximum we can write, or max not equals to null and root dot value is greater than equals to max. If any time it's going outside this boundary, whatever the current value is coming, if it's going outside of this boundary, then just return false. That's it. And the same thing we have to do for and now for each left and right subtree, we have to check this condition, right? So anytime we are going outside the boundary, return false, else it will be kind of returning true. So now just check all the left subtree and right subtree both time. So if bst root dot left, so we are going towards the left side. So for the left side, what was the condition to initialize min and maximum value? So min was whatever the minimum value is coming, and max is what root dot value, right? So if you are going towards the left hand side, the minimum we are initializing whatever the minimum has come, and the maximum it can take this particular value would be the root dot value. So that's what we did. Similarly, now each BST we need to go towards the right hand side as well. So root dot right. And now what would be the minimum and maximum value? So maximum, when we are going towards the right side, maximum value is this root dot value if you see. Sorry, maximum value is this maximum value. But the minimum value is this root dot value. So minimum value is root dot value. And maximum value is whatever the maximum is coming towards. So this is taking care of entire subtree, whatever in the left subtree we have and the right subtree, and for each of them, if any of time it's going outside the boundary, returning true, else this will return the false. And now we just call this function hbst, and now just pass this root. Instead of checking with minus infinity and maximum infinity, we are just checking with this null value right here. So we can pass the null for both min and max. Else we could have passed the minus infinity integer dot min or integer dot max as well. Now let's try to run this and see if there is any error, compilation error or something like that. Looks like it's going infinite. What is the condition? So we're passing the root value here and some min and max. Function is bst. Okay, it's got accepted. Now let's submit. Okay, so solution got accepted. So that's all about today.